When designing a finite state machine, consideration needs to go into the timing details of the clock signal. This video will explain issues that can occur with clock sources, including a discussion of clock speeds, different clock sources, and the use of asynchronous clock signals such as push buttons or keypads. First, let's define frequency and period. Frequency, which uses the symbol F, defines how many repeating cycles occur every second on a signal. For a square wave of the type used to clock a digital logic circuit, the frequency is a measure of how many rising edges occur every second. The unit of frequency is hertz. A frequency of 1 hertz refers to 1 rising edge occurring every second. 100 hertz would be 100 rising edges occurring every second, and so on. Clock frequency is a typical metric used when describing the speed of a computer or microcontroller processor. Period, on the other hand, is the reciprocal of frequency. Period uses the symbol T. T equals 1 divided by F, and vice versa. F equals 1 divided by T. Period refers to the length of time that elapses between subsequent rising clock edges. A frequency of 1 hertz has a period of 1 second. A frequency of 100 hertz has a period of 0.01 seconds or 10 milliseconds. While frequency is typically the metric of interest, delay paths are measured in units of milliseconds, microseconds, or nanoseconds. So it's important to be able to switch between period and frequency. Before I get into the weeds of timing issues, I want to point out the single biggest issue that you may encounter when building the types of circuits we used in this class. Our circuits are typically running at pretty low frequencies, so we're not typically prone to the issues I'll discuss in a few moments. But we absolutely can be bitten by disobeying the setup time of a flip-flop. If our input values change at the same moment as the clock ticks, then the setup time of the flip-flop is not obeyed, and the circuit will have issues. I'll discuss this at the end of the video when we discuss asynchronous clock sources, but I want to bring it up now just so you can put everything in this video into context. Let's consider possible timing issues with a circuit. Propagation delay refers to the amount of time it takes for the logic inside the flip-flop itself to form a valid output after a triggering clock signal is received. This value is typically available on a datasheet for a particular flip-flop. Another source of delay comes from any combinational logic used to generate flip-flop input values. There's no single number to use to represent this value. It depends on the logic used to generate an input signal. But if you know what logic gates are used to generate a signal, the maximum combinational delay can be calculated by determining the longest signal path and referring to datasheets to calculate the timing for each gate. Two other timing issues that have been previously discussed in this class are setup time and hold time. As a review, setup time is the length of time a signal needs to be stabilized on the input of a flip-flop prior to a triggering clock edge. Hold time is the length of time a signal needs to be stabilized on the input of a flip-flop after the triggering clock edge. These two values can be determined by reading a flip-flop datasheet. In general, the period of a clock signal applied to a sequential circuit cannot be less than the total amount of time required for previous outputs to be valid, based on flip-flop propagation delay, plus the amount of time it takes the combinational logic to stabilize, based on the combinational delay, plus any setup times that are needed. By summing those delays together and taking the reciprocal of that value, that represents the fastest theoretical frequency at which the circuit can be clocked. However, there are other considerations to take above and beyond this theoretical maximum. Clock skew refers to the fact that not all flip-flops in a circuit will receive a clock trigger at the same exact moment in time. Consider a circuit with two flip-flops. If the clock signal is applied to one point on a breadboard or printed circuit board, then the amount of time it takes to travel to each flip-flop will depend on things such as wire length, temperature, and whether or not other signal wires are routed close enough to the clock wire to cause possible coupling issues. While this difference is largely trivial in the types of circuits we build in class, it may impact a circuit if there's a big difference in path length from one flip-flop clock input to another. Clock skew is not uniformly a bad thing, but is a consideration that must be made when designing a circuit. Looking at our circuit containing two flip-flops, an issue known as a hold violation occurs if flip-flop 1 clocks first, updates its output, and subsequently causes the input to flip-flop 2 to change before the previous data had been clocked in. This issue cannot be solved by changing the clock frequency. In this case, we would need to ensure that the propagation and combinational delay times are both greater than or equal to any clock skew plus the hold time required on each flip-flop. Assuming that hold time is 0, if the clock skew between each flip-flop is 10 nanoseconds, but the combinational and propagation delay is 5 nanoseconds, then we would have a hold violation because the output of flip-flop 1 will change before flip-flop 2 gets clocked. However, if we select a flip-flop with a propagation delay of 10 nanoseconds and the input combinational logic has a delay of 20 nanoseconds, the clock skew is only 10 nanoseconds, so we can be sure that flip-flop 2 will clock the previous data before the new value becomes available on its input. Because clock skew now contributes to the overall amount of time it takes both flip-flop inputs to update, it must be included as a limiting contribution to the minimum clock period that can be used in a circuit. Overall, the minimum clock period is now equal to the propagation delay plus the combinational delay plus the setup time plus clock skew. The reciprocal of this value represents the theoretical fastest frequency at which a sequential circuit can be clocked. A thorough discussion of clock sources would make this video very long, so I'll link a blog post I wrote on the topic in the description of this video if you're interested. Otherwise, I'll just discuss the two most commonly used clock sources in this class. The first is a function generator. A function generator can generate multiple different voltage signals that can change with respect to time. Function generators typically have an output signal that generates a TTL clock signal, which is a square wave oscillating between 0 and 5 volts. There's not much to take into consideration when using a function generator, other than it's large and expensive. If you're building a circuit that requires a clock signal, and you want it to be small enough to fit on a single breadboard, then a function generator may not be an appropriate clock source. The second clock source is a 555 timer used in astable mode. This chip is small, cheap, and relatively straightforward to use after you get the hang of wiring it up. However, sometimes 555 timer chips have some glitchy outputs that may cause issues with your circuit. I see this occur frequently in design projects in this class. If you have a circuit that you're sure you've built correctly, but sometimes states in your finite-state machine or counter circuit are randomly skipped, then your 555 timer output signal may be to blame. To fix this, use a 7414 Schmidt inverter chip on the output of your 555 timer. This will correct any voltage levels to the appropriate TTL-compatible levels. Sometimes it's inappropriate to use a synchronous clock source such as a function generator or 555 timer. When a user is going to be inputting data to cause a state to change, it can be difficult to synchronize timing between a clock frequency and having a user enter data. For example, a finite-state machine that requires me to enter a particular sequence of numbers to unlock a digital padlock may have a clock source of, say, hundreds of kilohertz. But I can't necessarily enter data that quickly into the padlock. Either the finite-state machine will have to be carefully designed to test for new data entry, or the act of entering data into the machine can be used as the clock source. So by asynchronous clock source, I mean that we're using the depression of a push button or keypad button as the clock signal. Two big issues can occur when doing this. The first issue, as mentioned, is setup time. If I use a push button both as an input signal and also as a clock source, then the input value on the flip-flop will not be valid prior to the clock edge and setup time will be violated. The keypad encoder chip we have has an output pin that generates a rising edge when a button on the keypad is pressed. Using a keypad both as an input signal and as a clock source will similarly violate setup times. In these cases, if using an active high push button or the keypad encoder with the data available signal, the remedy is to use a falling edge clock trigger. In the case of the push button, once the user lifts their finger off the button, that will cause the flip-flop to clock. Because a human likely can't push a button faster than the setup time, this will ensure that an amount of time between valid inputs are present is greater than the setup time of the flip-flop. On the keypad encoder, the amount of time it takes the data available pin to go low again will also be greater than the setup time. This amount of time is not dictated by the datasheet of the encoder chip, but is related to the capacitor used externally when wiring it up. A capacitor can be thought of as an electrical device that causes voltage levels to change slowly rather than all at once. The second major issue that can be encountered when using a push button or toggle switch as a clock source is switch bounce. Switch bounce occurs due to a mechanical oscillation causing the contacts to disengage and re-engage possibly several times prior to settling on a steady state value. For example, when depressing an active high push button, the voltage may become high and low quickly several times before finally setting on the expected high value. Switch bounce for a push button can be eliminated in hardware using circuitry known as a low-pass filter. This will screen out any high-frequency voltage oscillations. Then, use the 7414 Schmidt inverter chip to ensure that the voltage levels are TTL compatible and maintain sharp, square wave-like transitions upon pressing the push button. Debouncing a push button is going to be vital if using it as a clock source to prevent multiple transitions to occur on a single press of the button. Fortunately, the keypad encoder chip uses internal circuitry with an external capacitor to debounce each key on the keypad. Debouncing a toggle switch is much more complicated and can be achieved using an SR latch. To avoid having to open this can of worms, I would recommend not using a toggle switch as a clock source. In general, a dip switch is a poor choice of clock source due to the impossibility of a human changing multiple inputs simultaneously. Say, switching an input value from 001 to 110. If a dip switch is to be used as an input source, then a debounced push button can be used as the clock. Using different input devices as input and clock would also take care of any possible setup issues.